All right, welcome back to part two of our series on demand-side energy management. And it's a great week to have this webinar as it falls right in the middle of National Environmental Education Week. Today's subject is demand-side energy management and the grid. We're going to talk about the electrification of the grid. We're going to discuss how we value and use infrastructure to optimize DSM. We're also going to get into topics like peak load reduction, advanced load shifting, grid optimization, distributed generation, and energy storage. And that last topic is something we touched on a little bit in our last webinar. We're also going to hear how construction codes, standards, regulations, and utility policy impact DSM strategies. And finally, we're going to take a look at existing DSM programs and how you might be able to work with your own utility. Back again to navigate us all through this three-part series is David Butler. He's a senior engineer who has more than 30 years of experience with control systems and electronic design. He has been published multiple times in industry publications and has presented at many trade shows. His memberships include the Illuminating Engineering Society, Association of Energy Engineers, Entertainment Services and Technology Association. He holds a LC certification, and he's also a certified energy manager and certified measurement and verification professional. And if all that wasn't enough, he also brings science back to science fiction under the pen name David Pax. Now, before we get rolling today, I have to tell you about PowerShift by NV Energy. They want you to know that you can never save too much energy or money. And that's why NV Energy offers PowerShift to help its residential and business customers conserve even more energy and save money on their power bills. PowerShift by NV Energy is also about providing you with excellent customer service. It's your one-stop shop to find all the energy-efficient products and services to help you boost your bottom line, along with convenient ways to manage your account. PowerShift Energy Advisors are dedicated to working side by side with business customers to discuss their needs and to find energy efficiency solutions that save money. Plus, their Business Solutions Center is the place to go to discuss your bill payments and account-related questions. For more information, please visit nvenergy.com/PowerShift. Now, during the course of today's presentation, you can submit questions for our guest. Simply use the questions box on the right side of your screen. We're actually going to stop a couple of different times during the presentation today to take your questions about the topic that we will have just been discussing. And we will also have the Q&A at the end of David's presentation, just like usual. David, if you're ready, so are we.
Thanks, Mike. And good morning, everybody, or I should say good morning for the West Coast where I'm located. Good afternoon for everybody else. And just to start off, we're going to recap a little bit of webinar one. Last time we talked about why demand-side management is important, and we talked about topics such as peak demand, when demand peaks occur, and some of the challenges that the changing energy environment can present for the future of the grid, such as the duck-shaped curve, where as we introduce more solar generation, we are not necessarily eliminating peak demand concerns, but we are shifting the time of day where they occur. And everybody needs to be aware of this because a lot of our decisions about energy infrastructure and energy systems within our buildings are going to be affected by the way that energy is generated as more and more renewables come online. So in this webinar, we're going to discuss the basics of how to implement specific demand-side management strategies. Last time we talked, again, high level, talked about how doing things such as lighting retrofits or HVAC updates can affect the demand in a building and how that shows up on the grid. But today we're going to get into some more technical detail, and there will be some slides where you'll see a little bullet point down at the bottom for questions. I'll go through that slide and talk about the general information for each of the topics. And then if you have specific questions, perhaps relating to your own facilities or facilities that you're working with, we can get into some specific questions about that topic when we get there. And as Mike said, he will be facilitating those questions. Next time for webinar 3, we'll go into more detail on advanced demand-side management topics, such as looking at new construction practices and understanding how to plan for demand-side management in the long term. So today's learning objectives are going to discuss how we plan electric infrastructure, how utility infrastructure expense impacts effective DSM strategies, peak load reduction, advanced load shifting and energy storage, distributed generation and demand-side management, and then how codes will shape activity with respect to demand-side management, and then existing DSM programs and how to work with your local utility. I'm going to use examples from Las Vegas, where I'm based, and where a large portion of NV Energy's customers are based in Southern Nevada. These specifics vary. They vary throughout Southern Nevada. They vary throughout the entire state of Nevada. So, for example, Northern Nevada may have some different transmission voltages than the voltages that are used here in Southern Nevada, where I'm located. And other utilities could have different voltages as well. So understand that specifics are going to vary even within utilities and certainly from utility to utility, but I'm going to use this as an example to help you understand a little bit more about how the grid and demand-side management interact. So the most common transmission voltage in Southern Nevada is 138,000 volts. And you can tell transmission lines because they use high towers, very tall towers with widely separated wires. And that's because at 138,000 volts, the wires need to be spaced far apart to avoid any potential of the wires on different phases touching, even if there's high winds or storms or anything that is going to move the wires around. Now, you will sometimes see on large transmission towers that two wires are run very close to each other. Those wires are on the same phase. They're just doubling up the wires to increase the capacity. It doesn't mean that they're on separate phases. Now, distribution voltage, again, for the most part, the most common one here in Southern Nevada is 12,470 volts. And that voltage can, again, vary quite a bit between different utilities. Could be as low as maybe as low as 4,000 or 5,000 volts in some cases, might be as high as 20,000 volts in some cases. In this case, it's mostly 12,470 throughout Southern Nevada. And distribution poles you can identify because they are typically shorter and the wires can be closer together. You can see distribution poles in some neighborhoods. As a matter of fact, our office here in the central part of the Las Vegas Valley has a distribution line running right down the street. And so I can see a distribution pole as I pull out of the parking lot every day. Substations are where we convert that 138,000 volt transmission voltage to distribution voltage for the most part. Again, it varies quite a bit. For example, some very large customers will receive transmission voltage directly at their facility, and then they would own the equipment to step that voltage down to the voltages that they are using internally. Typically, this tends to be larger industrial facilities or here in Nevada, mines that will receive transmission voltage directly. In the case of a mine where their operation may move around, or even in the case of, say, a large farm up in Northern Nevada, it may just be beneficial for them to have the flexibility of receiving transmission voltage at a single point, having that meter placed there, and then be able to adjust the distribution as the nature of their operations change. Now, this isn't something that's changing frequently, but of course, as a mine is working in a particular area, they're going to mine out material in one area and then move to another area. So it may be more effective for them operationally to be able to move those lines around. But for the most part, commercial buildings, residential buildings, all are receiving voltage that has come through the distribution system and through substations. And within each substation, there will be one or more banks of transformers. The typical bank here has connection for 4 12-470 volt circuits. So we've got that 138,000 coming into the bank, and then that's being distributed out on 4 12-470 volt circuits that have a maximum capacity of 600 amps. So when we start to look at new construction or expanding capacity within an area, the planned circuits are evaluated for their peak summer load. So they'll look at each circuit, go back and look at the history of the peak demand on that circuit and look at how close it's getting to that 600 amps. When the peak load on a circuit in the previous summer has hit 550 amps, then they need to add a circuit to the bank. So they'd start with just one of 4 12-470 connections coming out of that bank, and then add another circuit to that bank when the first circuit hits that 550 amp level. And the reason for the 550 amp target is that you need to have that overhead, that excess capacity, so that if the summer peak last year is not reflective of the summer peak this year, in other words, this year it's getting hotter and perhaps there's been some more buildings added to that circuit, so you need to make sure that you're not going to trip out that circuit and lose the whole thing if we have a particularly hot day. So at the point where the previous year's peak summer is at about 550 amps, then a new circuit is added. So where this ties in with demand side management is that DSM strategies reduce the peaks on the circuits. And there's a number of different ways that this can be done. This is going to outline the next several slides, and then I'm going to discuss the details of each of these technologies on the following slides. So a basic lighting retrofit can reduce overall demand. And if you have several basic lighting retrofits that are done in buildings that are on one circuit, that can help keep that summer peak below that 550 amp threshold where they would need to add a new circuit. As you can imagine, adding a new circuit and splitting out the distribution, restructuring things is a very expensive proposition. It's a lot of equipment, it's a lot of labor. So if demand side management can reduce that summer peak to the point where it can delay the need to add circuits to that bank, then that's better for everybody because the cost savings then go back directly to the ratepayers. So basic lighting retrofits reduce overall demand. Above and beyond that, there's programmable lighting controls that, in addition to reducing demand, overall can reduce it at specific times. Programmable thermostats can provide basic demand management and some ability to reduce demand at specific times. Advanced demand management, which we discussed a little bit last week, can reduce the coincident demand peaks. So those are the times where we have several different air conditioning units or perhaps process equipment and air conditioning units that are all starting up at the same time and creating that large demand peak. And then advanced lighting controls. So this goes above just programmable lighting. Advanced lighting controls can provide, in addition to energy savings and demand management, productivity improvements. And that's a very, very exciting area. This is a very new area, and we're going to talk about that here in a couple of slides. So let's start with the simplest, and in some ways, one of the most effective, the biggest bang for the buck, if you will, which is a basic lighting retrofit. Before LED lighting, the typical percentage of lighting energy in commercial buildings was 25 to 30%. That was a national average. Today, when you're looking at new construction, new builds, it's 6 to 7%. And that is primarily due to the change of technology to LED lighting, which is quite a bit more efficient than previous sources. It's quite a bit more efficient than most fluorescent lighting, and considerably more efficient than incandescent. These are averages. It varies. Healthcare, for example, has quite a bit higher lighting energy use and continues to have a higher lighting energy use even with LED fixtures. And that is something that is easy to understand, right? You have a lot of lighting in patient rooms, you have lighting in operating rooms, hallways, offices. You just need a higher level of light in the healthcare environment than you do in, say, a typical office. At the other end of the spectrum, places like warehouses don't really require a lot of lighting, and a lot of times warehouses are able to use daylighting to provide a lot of the light that they need. So their lighting energy use can be quite a bit lower. Now, when you're looking at doing a basic lighting retrofit, any upgrade will help improve the performance. But it's always best to go for the biggest upgrade that you can get. So for example, if you simply are doing a typical T12 to T8 upgrade, you might save 20% of overall lighting energy. That's good. You're still saving 20%. But if you upgrade from T12s to LED fixtures, you might save 50% of overall lighting energy. And so you need to look at the way that your building operates and what you're trying to achieve with these lighting upgrades in order to decide whether you want to just do the lowest cost option or whether you're able to do a bigger step, a more sophisticated upgrade that is going to save you more energy and pay back more over the long term. Now, if you can do a larger upgrade, that reduction in your base load may also help reduce your peak demand, because even though the air conditioners and the process loads may be switching on at the same time, the base load has been reduced, and so your peak demand has also been reduced at that point in time. But unfortunately, there are many times where we'll see that one reduction in energy use is then offset, where somebody will just do a lighting retrofit and then say, okay, great, I don't have to worry so much about this. And their peak demand, therefore, still can wind up being just as high, even though they've reduced the base load. So we'll just pause here for a moment about any questions about basic lighting retrofits.
Well, I don't see any questions at the moment coming in from the audience, but as I am also sitting and paying attention to this, I did have a question. We touched on this a little bit in the last webinar. Is this really where the occupancy sensors start to come into play a little bit?
That, in fact, is under programmable lighting controls. So that leads in perfectly.
Okay. All right, great. Because I knew we touched on that. I don't know if it was my question from last webinar or somebody else's, but I know occupancy sensors was something that came up, and we said we'd discuss it in this one. And so I'm curious if nobody else is. I know I am. Not just on the lighting side, but also if there are occupancy sensors on the HVAC side too. So I'll let you get to that in the natural progression of today's presentation.
Perfect. So, as Mike mentioned, we are seeing more and more requirements for occupancy sensing, programmable lighting controls. They are now required by code for new construction and major retrofits in most parts of the country, certainly here in Southern Nevada, where as of February 4th, we are on the 2018 International Energy Conservation Code. There's two major codes that are used in the United States, and they're called model codes, and that's the IECC, International Energy Conservation Code, and ASHRAE 90.1. And the reason they're called model codes is that they establish the general language that will be adopted by each individual jurisdiction, but the jurisdictions can make minor amendments to the code as they are adopting it in order to tailor it for their particular needs. So for example, here in Southern Nevada, we are primarily climate zone 3B, but we do have some mountains around the Las Vegas Valley, and up in the mountains, the climate zone is actually a 5B. And so we'll make that adjustment to the code as it comes through. Also, there can be some changes in definitions. For example, for several years, the Southern Nevada building officials would add a definition for a casino gaming floor, add clarification of it, because you may or may not be aware of the fact that there's a lot of casinos here in Southern Nevada, in Las Vegas, and so we wanted to make sure that there was a very, very clear definition of what a casino gaming floor was, because the way that casino floors are built, there's a lot of different types of spaces that are all integrated into the floor. So you can have center bars that are right next to slot machines, and slot machines in the center bars, and then gaming tables for poker and blackjack, and so on. And so it was very important to have a very, very clear definition of what a casino gaming floor constituted. And that's another example of the type of amendment that a model code would receive as it's adopted by a particular jurisdiction. Now, part of the interaction with codes is that we're seeing more and more LED fixtures required by the codes, but they're also becoming much easier to integrate with the lighting controls. So for example, if you are purchasing a straight LED troffer as opposed to a fluorescent troffer that you might then add LED lamps to, the pure LED product is typically going to come with a 0 to 10 volt driver that makes it easy to tie in with, say, daylight sensors, because it has that 0 to 10 volt dimming built in. It was always possible to dim fluorescent fixtures going back decades, but it wasn't common to do it. It was a special order item to get a 0 to 10 volt dimming ballast for a fluorescent fixture. You could do it, but it wasn't readily available. Whereas most LED fixtures will come with some form of control integration, such as 0 to 10 volt or Dolly or DMX512 as a standard option. And so that means that it now becomes easier to meet these code requirements for programmable lighting controls, because the fixtures can now just connect directly up to the devices. So that enables a variety of control strategies. The most basic one is scheduling or time-based. Working in energy management, it is surprising the amount of time that fixtures are simply left on when they're not needed. And implementing a schedule can help save quite a bit of energy just from shutting off the lights when spaces are not needed, say because a business is closed. And this is now also required by the code. There's also occupancy or vacancy-based sensors. So this is where instead of scheduling a space, there are sensors that are detecting when people are present in the space. The difference being that occupancy will turn the lights on when they detect people and turn them off when they no longer detect people. Vacancy starts by requiring some sort of activation. So you walk into a room, you hit the button, that will turn the lights on, and then vacancy sensing will turn the lights off when it no longer detects people in the room. And that is required more and more. For example, Title 24 in California requires vacancy as opposed to occupancy in many places. Then there's task tuning, taking advantage of those dimmable fixtures to reduce the overall light level to the point that people are comfortable, but you're saving as much energy as possible. And that will depend greatly on the age of the population within the workforce of the building. Younger people's eyes are more sensitive to light than older people. And so if you have a very young population of workers within a building, they may take the light down to a very low level. There are some buildings that I've been in for internet-based companies, have a lot of young workers there, and frequently they will simply have the artificial light turned off and simply work with the light from the windows and from computer screens. As we age, say between about the age of 20 and 50, our eyes reduce the amount of light that they receive. Every year as we grow, a new layer gets added to the cornea, and over time, that compound addition of multiple layers reduces the amount of light that's actually striking the retina. So by about the age of 50, we've reduced the amount of light that our eyes are receiving by about half. And so in the built environment, we need to compensate for that by increasing the light levels. That's what we mean by task tuning. And you just reduce the light levels until people start to complain, and then step it back up just a little bit, and now you're saving as much energy as you possibly can. Fine-grained control, also known as personal control, it has been found that by providing people the ability to have some control over lighting in their areas, they will typically reduce the amount of light, and so by giving them that control, it can also save energy. And then there's daylighting. That is required now by codes where lighting that is near windows or near skylights has to have a separate set of sensors that will allow the lights to be dimmed when there's sufficient natural light in the space. And then there's demand limiting, where on a signal from a controller, the lighting can be reduced by a certain amount, and that then allows for a reduction in energy on a time basis that is coming from a remote signal. This all allows us to reduce that peak demand through programming. For example, setting a threshold that triggers demand limiting. So any questions here about programmable lighting controls?
If anybody does have any questions, please send them in via the questions box. And I'll start off with a question. And I swear I have not seen your presentation. I don't know if I'm leading you into the next section or not, but payback period. I'm not a huge fan of the simple payback period because we usually bring it up in code development hearings and mortgages versus paying for cash, that sort of thing. But in this instance, some of these upgrades are probably paid for out of an operations budget or something that's not financed. Would that be accurate to say?
That's correct. And we also will get into utility incentives that can help to pay for these. Typically, the payback periods are fairly short, and you're correct. The simple payback is not the best way to evaluate, but because it's quick and easy and very understandable for people with a wide range of backgrounds, it is commonly used, where we simply look at the cost of the lighting controls, the expected energy savings as dollars, and then look at how that divides out and how many years it's going to take to have that simple payback. But certainly, when we get into larger projects in particular, we don't just use simple payback. We will look at things like net present value and other financial measures to understand precisely how this is going to affect the operation of the building over time.
Okay, yeah, that's kind of what I was going was if there was any information on the cost of upgrades versus on-bill savings. But again, where applicable, right? You know, if they're financing it, then that's not. If they're paying for it with cash or something, that's a little bit of a different story. So I appreciate you hitting on that topic there.
Absolutely.
I don't see any other questions from the box, but go ahead, David. Sorry.
Okay, so let's talk about programmable thermostats. Now, a basic programmable thermostat that is not networked will still allow you to set schedules, and that's good, right? Because even more so than lighting, which of course people will see if it's left on and sometimes turn off, thermostats frequently do not have an automatic setback if they're just a very, very basic rudimentary thermostat. So a programmable thermostat that allows you to set a schedule and allows you to do a temperature setback during unoccupied hours can save quite a bit of energy. But if you can network the thermostats, then it gets even better, because that now allows for remote access, gives you the ability to manage set points throughout the entire building, as well as get remote monitoring and participate in demand response programs. So you will reduce the base load in part just through more efficient operation, but you also may reduce peak demand. And let's take a look at how that works. So this is from a building that is participating in one of our NV Energy programs, and I've anonymized it here, just taken a screenshot of the specific data here. You can see that from midnight to 5 a.m., the set point is at 84 degrees. So when the space temperature is there at 78, 79 degrees, the air conditioning isn't running at all. And that, of course, is saving quite a bit of energy compared to what would happen if that set point had been left at the 74-degree temperature that it's at during the day. Then at 6 a.m., it steps down. And those of you who were attending the last webinar will remember that early morning startup where we showed that big jump that can happen early, first thing in the morning. This is how you avoid that. Instead of jumping from 84 down to 74, at 6 a.m., this thermostat jumps from 84 to 77. So it does start to cool, but for example, it doesn't necessarily need to kick in both stages of the air conditioner, because it can achieve that 77-degree set point with just one stage and still be ready for the building to open at around 7 o'clock when people start coming in. So at 7, it then drops to the 74-degree set point, and we've managed that early morning peak, but we're still able, you can see from how quickly the temperature drops from 77 to 74, we're very quickly able to achieve the temperature set point that people find comfortable within that space. Now, this screenshot is from yesterday. So these are real-time or near real-time operations here in Southern Nevada. Later in the day, it's showing just a flat line because it trends out wherever the current setting is. Had I taken this at, say, 8 p.m., we would have seen the night setback shift back up to that 84-degree set point. And this is what programmable networked thermostats can provide you. These different set points could be provided by a programmable thermostat, but when they are networked and then we can get a remote internet connection, we're also able to see what's happening and to remotely change that. So this is a slightly larger view that also shows on this particular unit the supply air temperature. So the top graph is the same as the one on the previous page. The bottom graph is showing us 3 additional temperatures from inside the unit itself. And these come with an additional module that is an accessory to the basic thermostat. So the green line is the supply air temperature that is leaving the unit. The red line is the return air temperature, and you can see this kind of yellow gold line is the outdoor air temperature. And so you can see that the return air temperature did jump up a little bit when that set point shifted down to 77 degrees, and then it fairly quickly came down to temperature using some energy, but not as much as if everything had just slammed all the way to 74 degrees at 6 o'clock in the morning. This is an example again of the additional data that you get with network thermostats and the value in using this type of technology. So we'll pause here just for any questions about programmable thermostats.
All right, I don't see any questions at the moment. I'll send out another notice to everybody.
Okay. Well, we'll keep going then. Both lighting and HVAC, whether that's a central plant or whether that's a thermostat system, thermostat controlled system, can provide advanced demand management if they are configured to do that. Lighting can provide a very quick reduction, but it will be noticeable. So even if you have dimmable ballasts or dimmable drivers in your LED fixtures, if you change the lighting by 20% over 2 or 3 seconds, everybody's going to see that. So you can get a large energy reduction that is noticeable out of lighting. And before I said with LED, we're down to about 6 to 7% of the building energy. But if we reduce that by 20%, that's still going to be about 1% of the overall building load, which can be significant if we're talking about avoiding a demand peak. Now, it's not desirable to rapidly change the lighting like that, but it can be a decision that a facility manager and building owners and operators can make if there's a significant concern about the peak demands that the building is seeing. Now, a better choice with lighting is to do a long fade, say about a 5-minute fade of a 5 to 10% lighting reduction. If you do a very slow fade with lighting, 5 minutes or so, and a lower overall change, most people will not notice that. And so that's a way that you can have demand reduction that can help you avoid peak demand charges without having any impact. So lighting can give you both if you have the correct lighting controls installed. You also can get a quick demand reduction with small and medium-sized rooftop units where the temperature setback will simply cause the unit to cycle off, and that will reduce demand. If your building has a central plant or larger RTUs, they will require time to stage up and down. What we've typically found is that it can take as much as half an hour for a demand reduction within a space through temperature setbacks to show up in an actual reduction in electric demand on the central plant. So it'll take time for that to propagate, and if you're using that as part of a demand management strategy, you need to plan that in. So integrating the systems and setting peak demand thresholds is the best way to manage peak demand. You may not be able to do that cost effectively in smaller buildings, but in larger buildings, you can use a variety of different automated systems that will integrate using, for example, BACnet to connect into your central plant and to your overall HVAC and lighting systems, and will help manage that peak demand so that you're not getting those high demand charges that we discussed last time. So any questions here?
I don't see any coming in, but I did have one question. I think I'll probably save it until the end Q&A. It came to me after we got off the programmable thermostat slide, so I'll bottle that one up until the end.
We'll come back.
All right.
I will go through this fairly quickly, but the potential for using circadian entrainment in conjunction with energy management is, I believe, very significant. Now, we first really started to understand circadian lighting in about 2002, when researchers discovered a third type of photoreceptor in our eye. We all learned about how our eyes have rods and cones back in school, back in elementary school or high school. But in 2002, they discovered that there's a third type of photoreceptor that is wired directly to the hypothalamus in the brain. It does not provide any sort of visual signaling. It simply provides circadian entrainment. It's sending triggers to the hypothalamus to help regulate our bodies. So what we've seen emerge in about the past 5 to 10 years has been circadian lighting, which simulates daylight indoors. By using circadian lighting, you go to a bluer and brighter light first thing in the morning and early afternoon, a warmer light at a lower level later in the day. And by simulating the natural daylight cycles, they have found productivity improvements by as much as 20%. People are more alert, they're more comfortable, they're happier, and so productivity environments of as much as 20% have been demonstrated. And this even goes back to using fluorescent lighting, not just LED. LED has just made it that much easier to achieve. They've been finding productivity improvements when using circadian lighting. Now, that also means that there's an energy reduction throughout the day, because the maximum lighting energy is only used for a few hours each day. Instead of turning on all the lights first thing in the morning and just letting them burn at that same level all day, they're being reduced. So that is providing energy savings right there. And when doing circadian lighting, there's a natural demand reduction in the afternoon, when in most places we start to see an air conditioning peak, because the heat loads in the building have been accumulating throughout the day and the outdoor air temperatures have been increasing. So the air conditioning needs to run more in the afternoon, and this is the time when the lighting can be reduced. So questions?
That's fascinating, the circadian thing. As I did not know that or wasn't aware of that. And so how do you, I mean, I guess the lighting controls, you can kind of balance that if you also have either skylights in a factory or warehouse, or large windows in an office setting, then you can kind of help modulate that?
Correct. The systems typically will use a combination of sensors and scheduling to determine when the lights should be bluer and brighter and when they should be warmer and dimmer. And if, for example, a cloud goes over, then the light sensors will bring the artificial illumination up to compensate, so that you maintain a set level within a building.
I guess I have one other question, and that would be, in the setting of, let's say, a factory where you have not just a traditional 9 to 5 shift, but let's say you have a 8 to 4 and 4 to midnight type shift. Is that something that would not apply then, or would they actually run that cycle twice then? How would that work?
So there's still a lot of research being done on second and third shift, but circadian entrainment can help with that. In essence, yes, they're simulating day, even though it might be night, but you do have to be more careful of it. I'm greatly oversimplifying here, but you do have to be more careful of it when in particular doing circadian entrainment on third shift. But it certainly can help, and it can help people adjust. The lighting can help people adjust from, say, a weekend where they'd have a normal daytime diurnal routine to going to work third shift and having a night-based schedule.
Okay.
This is an exciting area, but still a lot of research to be done.
Gotcha. Okay.
Something that has a lot of potential. So now we're going to talk a little bit about energy storage and then bring this all together. There's several different energy storage strategies. There's renewable firming, where you're simply maintaining the energy supply, say if a cloud goes over the solar panels. Then there's peak demand management, where energy storage is used to help level out the demand peaks, to help keep you below that demand threshold. Now, that right there is an area that readily connects with demand side management, because you can both shed load and use stored energy at the same time. The systems just need to be configured to know how to prioritize that and what source to use to help mitigate your peak demand at any particular time of day. And then there's load shifting, where you may store large amounts of energy when energy cost is low, and then use it during higher cost periods. So the important thing to look at with energy storage is how the energy is being used at the point of load. And that will then help you identify what sort of energy storage we're using. It's not always electric energy storage. Electric demand, such as lighting, you would want to use electric storage or chemical batteries to store the energy. But if the energy that you're trying to modulate is a thermal demand, such as heating or cooling, air conditioning, for example, here in Southern Nevada, then thermal energy storage may be a better choice. If the source of your peak demand and your higher energy bill costs is primarily due to air conditioning, then thermal energy storage could be a better choice for your building. And then also looking at commercial and industrial processes such as compressed air. A lot of factories, a lot of industrial buildings use a lot of compressed air in their manufacturing processes. And in some cases, adding storage could wind up not only mitigating peak demand, because you can store some air at times of lower demand and then use it later on, but it also can help improve the process, because most facilities do not have enough compressed air storage, and that winds up with variations in process that can wind up having other cost implications. You do need to consider storage losses, how much it's going to take to put energy into that storage at the time when it's available, and how long that will endure. For example, chemical batteries, every time you do a round trip cycle, you reduce the capacity by a tiny amount. We typically figure about 3% a year capacity reduction in chemical battery storage. So you do have to consider those losses, because over time you're going to have less capacity available, say, with a chemical battery. And then, Mike, as you were referring to earlier, you need to calculate the return on investment for different strategies. You don't just make a decision by saying, well, air conditioning is our biggest peak, so we're going to use thermal storage. Look at the return on investment for the different strategies. Just make sure to include thermal energy storage if air conditioning is the source of your largest peak. It may well turn out that thermal energy storage then does have the best return on investment, but check a couple of different options to make sure that you're choosing the best one for your building. And be sure to look, turn the stones over. Look at the different ways that you're using energy in a building, because the best use may not be the most immediately apparent. If you have excess solar generation, water heating may be a good way to store that. You can get grid-enabled water heaters now that will store water up to 170 degrees Fahrenheit, and then they have a tempering valve to bring that down to the desired supply temperature at the outlet of the water heater. And so you can essentially heat that water up to a much higher level if energy is inexpensive, such as around solar noon when you've got peak solar generation. And then you can store that in the tank and use that hot water throughout the day, or even perhaps as far away from the solar noon as the next morning. And it could be a good choice because hot water typically is a year-round load. So that's where you need to look at the return on investment. The ROI may show that water heating is better than, say, ice storage for air conditioning, simply because it is year-round as opposed to ice storage being primarily needed in the summer. On the other hand, if your peak demand is really significant during the summer, ice storage could be your best choice, but the ROI is going to tell you that. Distributed generation can take different forms. On-site for residential or commercial means that it's located on a customer's property, and that typically net metering is going to be used to return excess power to the grid. Now, you could use demand-side management to reduce the amount of power consumed in the building, but there's limitations to how much you can put back onto the grid. First and foremost, solar noon, everybody's solar panels are generating. And we've even seen times where at solar noon, the energy cost is negative, as in the utility will actually pay you to consume energy because there's so much solar energy available on the grid at solar noon. You also need to look at the time of use basis when you're considering distributed generation, because looking at the cost of the demand-side management measures compared to the benefits of the generation may or may not pencil out. Again, you have to go back to that return on investment. The example I use here is that curtailing air conditioning at noon isn't going to do you a lot of benefit, provide a lot of benefit, because your peak air conditioning demand will probably come later in the day. If anything, at solar noon, when you've got a lot of distributed generation, you should be lowering set points by a small amount and pre-cooling the building so that the building itself can coast through the afternoon for a little bit and help level out that late afternoon demand peak. There's also distributed utility generation, and that generation is owned by the utility but located close to the point of demand. It's not just a large generator in a remote area. And many times that also is going to include some storage. I'm going to save the questions here so that we can get through the last couple of slides, and then we'll take the general questions. Energy codes to continue to get tighter and tighter. Building envelope requirements for insulation continue to get tighter and tighter. We get less air exchange, better insulation required. We're seeing that the HVAC equipment requirements are getting more and more stringent. They have to be more and more efficient. and now are requiring things such as economizers. And lighting. Between 2012 and 2018, the average lighting power density requirement across all the different categories of lighting was about 35%. So the lighting is required to be more efficient, and we're seeing more and more code requirement for use of automatic controls, such as occupancy sensors and daylight sensors. The lighting controls are now required in most commercial spaces, so what was innovative 20 years ago is now standard and required. And California, for example, now requires that you have the capability to participate in demand response, although many people have not yet signed up for demand response programs. Where this affects the rebates is that the utility rebates are often based on the current energy codes as a baseline, and so as the energy codes get tighter, the baseline that's used to calculate the incentive payments is changing. However, on the plus side, requiring the ability to participate in demand response has lasting benefits, because most utility programs that integrate with demand response are ones that you can sign up for and leave as it fits the needs of your business. I'm not recommending that, it's just something that if you have the technology installed, you have the option available to participate or not participate as your business requirements change. So most utilities have programs to assist customers with conservation and demand management. These vary from a basic prescriptive incentive, such as a certain number of dollars per occupancy sensor, to fully custom incentives, where you come back to the utility with a plan for how you'd like to save energy, and then they will calculate a custom incentive for you. Be sure to ask questions, because there are frequently different technologies available in both the residential and commercial areas. And there may be separate incentives for installing renewable generation or storage. So be sure to ask about whether there are separate incentives available if you're also looking at doing generation, on-site generation and storage. So here in Southern Nevada, or actually all throughout the state of Nevada, we have PowerShift, and PowerShift is what is sponsoring these webinars. So this is just a quick screenshot of what you would see with the PowerShift page. This is your first step to start engaging with PowerShift here in Nevada to do a lighting retrofit, to get thermostats. You would start with nvenergy.com, save with PowerShift. You can play the video if you want to learn more, or you can jump directly to smart thermostats or discounts on newer, higher efficiency air conditioning. And you also can, if you were to scroll down on this page, you would see that there's an area for commercial incentives where you can apply for either the prescriptive or custom incentives for your business. So I think we're pretty close on time here. So rather than reviewing the conclusions, I'll open it up for questions.
Great, thank you, David. And like you said, if you have any questions, please send them in via the questions box. I'll go ahead and start. So the question I had said I would wait till later, you talked about programmable thermostats earlier, and I know that you know, we may not be talking necessarily about single-family homes. We may be talking about larger facilities, but where does something like Nest or those types of thermostats fall on that spectrum? And does anything like that exist for commercial or industrial applications?
So the commercial programs are typically using a somewhat different product than residential. You mentioned one brand, Nest, of typically residential thermostat. That might be incentivized with a rebate, or People might choose simply to purchase a smart thermostat on their own volition and then just achieve the bill savings that that thermostat would provide. But typically with a commercial program, the thermostat will be provided by the utility. And for example, with PowerShift, the thermostat is free and the installation is free. So there's no upfront cost to the business to get the thermostats installed. And then the customer retains all of the on-bill savings from the more efficient thermostats. So for example, if you don't currently have a smart thermostat with a schedule and then participate in PowerShift and get the Pelican thermostat, which is the one that PowerShift uses for the commercial projects, the Pelican thermostat allows you up to 12 schedule changes a day. So you can do that type of staging that I illustrated earlier in the presentation and save a considerable amount of energy.
Okay. I had one other question. It's kind of more of a philosophical type question, really. Let's say you have a large facility, a large building. It could be a warehouse, could be a factory, it could be a shopping mall, whatever it is. But it's got a large roof area, and you decide, okay, I'm going to install a lot of PV. I'm going to almost cover this roof with PV. Mm-hmm. Do you foresee a day where building owners could do that and use that install almost like community solar? I know it's a little bit of a radical idea because the concept of selling power from customer to another customer or neighbor to a neighbor is a little bit out there, but I base it off of something that is actually in existence on the water side, where the San Francisco Public Utility Commission has authorized, and I think it's been for like a couple of years now, the sale of captured rainwater from neighboring building to neighboring building. And so I'm just curious if you think we would ever at some point see that on the energy side.
So the technology already exists to do exactly that. The issue comes with the policy, and the policy is quite a bit more complicated than the technology in this particular case. As we're finding more and more, it's human factors that really matter with adoption of technology more so than the technical capabilities at this point in time. And so that's really what we need to start discussing and debating within the political arena, because on the one hand, it seems like it would make sense, hey, if I have excess energy, I just sell it to my neighbor. But there's a lot of policy issues that come in there, particularly related to pricing. For example, the building owner might have excess energy right now and want to sell it to the neighbor, say, to the south. And then maybe the neighbor to the north might come in and say, well, I'll pay you an extra 2 cents per kilowatt hour. And how do you manage that relationship? That's where the policy comes in. I'm again oversimplifying because this is a very complex issue, but it is something that we need to be very deliberate about as we look at it. Personally, what I favor is having the utility manage that, because the utilities are already set up to manage that. And having that sort of direct building-to-building sale of power, I think would wind up getting to be very complicated if you don't have the utility involved to help manage that whole infrastructure. And I'm also oversimplifying in terms of the way that would impact the grid, the way that it would impact all of the existing infrastructure, the way that the costs of the existing infrastructure would have to be managed. long and the short of it, yes, it is conceptually possible, and the technology does exist to do it, but we need to really think out how we're going to manage that. And in my opinion, the utility still has a very important role as we look at more and more distributed energy.
Yeah, that's a great point. Yeah, I didn't think about the almost the auction style bidding that could occur. I didn't really think of it from that side of things, and I don't know how it's handled when it comes to the water precedent that I talked about earlier. So it's a great point. I guess it's encouraging to know that the technology exists to be able to do it, because I could see it being a potential revenue source for building owners, potentially, right?
In principle, but the big picture still has to be managed. So, for example, the utilities have to comply with the requirements from FERC, the Federal Energy Regulatory Commission, and that is why we have stable power. That's why here in the United States, unless there's some kind of a disaster or an emergency, when we hit the switch, the lights come on, or the microwave starts heating our food, we have a very, very good energy environment here in the U.S. That is providing a very stable and reasonably priced energy supply. And as we look at more distributed energy resources, that changes the picture a little bit, but we want to be sure that we don't lose the quality and reliability of the energy supply as we start to introduce the capabilities of distributed generation. And there are a number of different models. I mean, there are, in some cases, for example, utilities that will build solar farms on roofs of large buildings, and it's utility owned, and the utility is basically leasing the roof and then managing the generation. I think that model works very well. But other buildings might want to invest in adding solar at their own expense, and then look at either recovering that expense through reduction in their own energy bills, or perhaps even selling the energy. But then that needs to be managed in a way that helps provide a reliable energy supply.
Gotcha. Okay. Well, I don't see any other questions, David, so I want to certainly thank you for setting aside some of your time today to talk about this with us. We really appreciate it, and we thank our audience for attending today. This was part 2 of a 3-part series that NV Energy is very generously sponsoring, so we thank everyone for that. And as I said, this is part 2, so where is part 3? Well, part 3 is right here, 2 weeks from now. We're going to delve into the third and final part, which is called Building and Design Best Practices for Optimized Demand-Side Energy Management. That's going to happen May 8th, and it'll start at our usual time of 2 p.m. Eastern Time. Until then, I hope everyone had a great Earth Day this past Monday, and that you all were able to enjoy the outdoors, and we'll see you all again real soon. Take care, everyone.